Okay, hello everyone. Welcome back to Kids Python Challenge. Okay, let's see what we were doing, or let's remember what we were doing last time. So we were revisiting prime numbers. So we first remembered how we did the prime number identification in lesson 25. And then we tried a presumably faster algorithm called sieve of Eratosthenes. Okay, and quickly check that they give the same answer. Okay, so the homework was tried up to 100 and check the results. Maybe, so let's go back to the code, open the file, connect, and maybe we can kind of make prime number identification algorithm and make a function out of it. So here, for example, we did divs definition and then used it as prime numbers identification, right? So for example, if find let's call it lesson 25 L25 prime P, okay, that's the name of a function up to n, is to call divs. Okay, let's quickly check how div function returns. Okay, so primes divs of 24 will return. Okay, let's see, it doesn't work. What is divs n the return L? That's strange. Divs 24 should answer. Oh, I see. As soon as it finds out it's longer than 2, it stops. So L25n will use this function to find out. Okay, let's find out find out primes up to n. Okay, so for I in range I 1, 2, it starts from 2 to say n, to say n plus 1, and then if divs I is equals to 2, okay, so here we start with an empty L, maybe PL, prime number list, empty, and then if the return value of the, it's the length of return value of I, which is 2, then PL append I, and after doing that, return PL. Okay, I think this will return all the primes. Let's check that. So for example, okay, let's run this box, define it, and see if def L25 P up to 100 returns. No, what we need is print returns correct answer. Okay, 2, 3, 5, 7, 11, up to 89, 97. I think it's correct. Okay, this is the first one. Okay, the other one is, as we saw, this is the function Eratosthenes, series of Eratosthenes. So let's define, using this, let's define erato function, which returns, for example, diff erato. Let's use ulim here. And then shift here. Okay. So first prepare ulim number of zeros, and then using this sieve of eratostiness, use up to use the function, and then maybe here after finishing the loop, okay, we use this. Okay, let's copy this and paste it here, and maybe this is good. So prim L2 prim L, okay, just like last time. PL is empty, and for up to UL, if NL is 0, then PL, append L, and then finally return PL. Okay, just to make that they are different, let's use different names here. Okay, so let's define it and make sure that this function, erato 100, returns the same thing. Okay, exactly the same answer as last time. Okay, right. Okay, so using these, try up to 100 and check the results. We check that they are the same. Okay, to do that, maybe we can do it as PM1 equals lesson 25 method, and PM2 equals erato method, and see if they are the same. Because it returns true, they are exactly the same. And that's true for maybe, hopefully, bigger numbers. So let's start today's part. Compare the two approaches, naive lesson and eratostiness. Compare the results up to 10,000 and also compare the processing time. Okay, so maybe we can do this as here. Maybe this is just as we did with the happy number. We prepare ulim list of, say, 10. Now we can start with 100. Arbitrary 100,000, might be 5,000, 10,000, 5,000. Shall we do it? Maybe we can do it. Okay, let's stop at 5,000. And okay, let's call it prepare a result PL1 no prime count. Maybe we can just count the number of primes. So PN1 list equals empty. And also, before that, maybe before we forget, import time, because we need to measure time. And time 1L equals, okay. So using this list, how can we do the ulim in ulimL? Okay. We do, let's see, let's call the first one L25P. Okay, L25P up to ulim and return the time. But before that, we need to process time. So s time equal time dot time, and then we record pn1 equals and this, and we pn1l append. So we keep track of the number of primes, okay, pn1. And also to measure time, e time, elapsed time equals time dot time minus s time, and add it to time1 list. And then print, maybe here. Okay, let's change the order to here. And then before that, let's print length of pn1, el time, okay, for ulim. So let's see it, how this works. Let's see, for 100, before under 100, there are 25 primes. Under 1,000, there are 168. Under 5,000, there are 669. Under 10,000, 1,229. And for 50,000 case is taking time. Okay, it took 12 minutes, 12 seconds. Okay, so let's copy this and do it with the erato function. So name it 2, name it 2, okay, and call it erato, and put it in pn1. So maybe this is fine. So just copy it as pn2 and t2. Okay, almost the same code. Maybe we don't need n here, 1 here. That's another big problem. Okay, so let's see it. It's pretty fast. It takes only 10 milliseconds, 17 milliseconds to do 50,000. And you see exactly the same. 5,133 up to 50,000. Okay, so now we check that Erato gives the same answer as less than 25 naive method. Okay, good. Let's visualize the speed up. So you know how to visualize the speed up. Okay, so here, do you remember that? Maybe you can use the code as last time. We copy and paste here. And then what is for x? X is ulimL. Okay, ulimL. First is timing method. So T1L. T1L in blue. And if we copy it, T2L for, say, red. So Erato for red and blue for the first one, naive method. Let's visualize that. What's wrong? Matplotlib, it should be fine. Okay, okay. So as you can see, the red lines are almost down here. Okay, there's no growth. It's so fast. Okay, let's change it to, let's change the x scale to log scale. Okay, and see the difference. It's even the difference. And if we change the y scale to log, we can see that I don't know what. Okay, yeah, it's like this. So Eratosthenes is quite fast. Okay, fine. So using Eratosthenes, sorry. So we saw that first method, it took so much time. Like for 50,000, it took 22 seconds. So we cannot go even further. But for larger numbers, maybe we can try even longer. So let's copy this and see how we can go from here. To do that, maybe we can continually arrange this, add more, like how about going from here up to 100,000, 500,000, and maybe 1 million, and say 2 million, maybe 5 million. Let's try that. If it doesn't stop, you continue that, and let's keep it. And also, because it's interesting, let's see the ratio of prime number up to the ulim. It might be interesting to see this. Okay, let's continue. Let's run it and see what we get, or if we can finish this. It's still running. Okay, for 5 million. Oh, it's done. It's quite fast. Okay, even for 5 million, it took only 3.6 seconds. Okay, we can go even further, maybe. So let's copy this. And see 10 times, even larger. Okay, let's see it. So up to 2 million, 5 million. Okay, how about 10 million? 10 million, okay, 10 million, 6 seconds. 20 million. Okay, while we are running this code, let's go back to the slide. Okay, what is the ratio of prime numbers for larger n to the power of n? Okay. It's still running. Okay, so let's prepare the, maybe it might be interesting to calculate the import math. And you know what, if you have, for example, math.log will give kind of number of digits to that number. For example, for 1 million, let's see, can we use this? Okay, that's right. So log of 1 million with the base of 10 gives 6, which means 1 million is 10 to the power of 6. Okay, so actually, if we use this function, it's almost the same as how many digits does the number have. And do you know what the relationship with this, with the larger n? That's interesting. So as we saw, the time ratio goes down as we go further with the larger limit. Okay, from let 2.25, 1.6, 0.8, 0.6. So is it going down all the way? That's an interesting point. So maybe you can check that. To do that, you can check, multiply the ratio by the log of large n. And that's something to do with a very important mathematical theorem called PNT, prime number theory. So if you're interested, please study and find out more about PNT and see if you can prove something about this. Okay, we'll come back to this topic next time. Okay, that's all for today. Thank you very much. Bye-bye.